Hi there, we're looking at Math 7, Unit 1, Lesson 11 today, talking about scales without units. And so we're going to explore different ways to express scales. And you began today's lesson looking at, for example, a map of a park says its scale is 1 to 100. And what it means without units is it means we're not saying centimeters, feet, and things like that when we're talking about the units. We just know that it's 1 to 100. And so you had a little discussion in class about what does this possibly mean to go from 1 to 100. And hopefully, if you talked about it in class, what it meant was if you had a scale drawing, for example, and we said this was 1 centimeter long and this one over here was 2 centimeters long, and when our scale was 1 to 100, that if this was the scaled copy, that the original, to go to the original, we would have to be multiplying all the lengths by perhaps 100 of the same thing. So the original would not be 1 to 2, it would be 100 centimeters and 200 centimeters. And so when we have a 1 to 100 scale, it means we're keeping the same kind of unit, but instead of 1, it becomes 100 of the same thing. That means we could substitute within there centimeters and centimeters, feet, and a variety of different things there. So that helps us get an idea for how the scale, what it would tell us about the measurements of the park. For the park, we would be saying, well, whatever drawing we have is 1/100th the size of the original, because we're reducing it down a bit there. From there, you moved on into, you had a picture of the Apollo lunar module. And you had a picture, and it said that the scale for this picture was 1 to 50. Okay, so let's see if I can back out just a little bit. But it said that the scale in this drawing was 1 to 50 was the idea for our scale for this drawing. So when you look at that scale, you were supposed to answer some questions related to what that scale, what does it mean in terms of the relationship to the height and the size of different elements there. So the first thing said, question asked if the legs of spacecraft are its landing gear. So these are our legs right here, or its landing gear. Use the drawing to estimate the actual length of each leg on the sides and write your answer in the nearest 10 centimeters. Okay, so we took a leg here and looked at centimeters, for example. We might notice that to go from the leg to the bottom of the leg, somewhere around there perhaps. Let's see, just draw it out here in a nice green here. That the distance from here to here is about 7 centimeters. Now that is in our scale drawing. But because this is a scale factor of 50, we would say we take 50 times 70 to get about 350, whatever that might be. In this case here, because it doesn't have a unit, if we're going to call this a centimeter, then this would also be a centimeter. So 350 centimeters is what the length of that would actually be. Okay, so that's kind of the idea there. So the leg there becomes like that. So if we look at number 2, it says use the drawing to estimate the actual height of the lunar module here, Apollo lunar module. So our height is this whole thing, and so if you include the antenna, you might be at about 15, 14 or so if you don't include the antenna. So let's not include the antenna. Let's go 14. That's kind of what my model shows. So we're going to go 14 being the height of this whole thing, not counting the extra dish on top. So we would say it has a height of about 14 centimeters. And again, because that is just a model, we would then say, well, let's talk about the actual height being 50 times that. So you'd end up with 50 times 100 times 14, sorry. So 50 times 14 ends up being 700 centimeters tall. Now, in terms of what that would be as a meter or something like that, if you wanted to convert that into a meter, we could say something different. We could say, well, it's actually going to be, for a meter, we would have to do a little conversion here. We would say that 1 meter is the same as 100 centimeters. And so we would do a little multiplication here using the factor there. So 700 times 1 over 100 would be 7, and we're left with the centimeters cancel out. So we've got 7 meters tall is the idea for how tall that would be if you're looking at meters, for example. You could do other factors or scales. You could use inches. You can convert things to inches. And so you would have done a variety of those things with your class today. The third question related to this said that Neil Armstrong was 71 inches tall when he went to the surface of the moon in the Apollo lunar module. How tall would he be at the drawing? if this drawing was drawn with his height to scale, and show your reasoning there. So if he was 1.4 inches tall, all right, 1.4 inches tall, let's take a look at this here. Well, what we're saying is we're going to have to take his height, then we're going to have to reduce that down quite a bit. All right, so in this case here, because we're starting with the actual and we want to go to the scale factor, because the actual was 71 inches tall and we want to do this 1 to 50, we're going to be going the other direction. So instead of multiplying by 50, we're actually going to be reducing it down. That means I could think of it as multiplying by 1 over 50, the inverse, or I could think of this as 71 inches divided by 50. So two ways of thinking about that. Divided by 50 is the same as doing times 1 over 50. And when I solve that, they both end up becoming 1.4 inches tall if I was to draw him on this scale. So that would look something like this. So if my ground is here, let's draw my ground. So he's standing on the ground. There's where the ground is at right there. Put him up there. So if he's there, he's going to be 1.4 inches tall. Well, there's a half is about there. That's 1.5. So slightly less than a half, maybe about here. Again, just estimating this here. He might be somewhere around there. And that's how tall he would be if he was the guy there. So that's what he would look like. Something like that. Probably be a little heftier than my little stick figure. And then the fourth one says sketch a stick figure to represent yourself standing next to the Apollo lunar module. If to do that, same idea, you just do your height, and you can do your height in inches divided by 50 or whatever it might be to find out what your height would be, and you'd be somewhere around here. You'd probably be a little bit shorter than Neil Armstrong, so maybe something like this, depending upon how tall you are as a student. So that was looking at the Apollo lunar module. And you probably spent some time then looking at this next question, which was a table that showed the distances between the various planets in the solar system. So it's talking about the different planets, Mercury, Venus, Earth, Mars, and the average distance they are. And so the idea was to find a spot at your school that you might be able to create a scale representation of the solar system itself. And so it depends on what you want to do. At our school site here at Alta Sierra, we have an amphitheater in the middle of our school that's in the shape of a circle. And so for us, that circle there, the distance from the center of that circle to the outer edge is about 60 feet. So if we wanted to create the solar system and have the planets walk around maybe the center point there, we would have 60 feet to work with that would allow us to figure out what that distance could be. So looking at just Neptune as an example, if I knew that Neptune was 2,800 million miles away, then my scale is I'm saying I want to make 60 feet be to match up to 2,800 million miles is what I'm kind of saying for this one here. This would be a really large scale, or actually a small scale compared to the real thing, but from that I could then reduce a little bit, maybe get that down to 3 feet is the equivalent to 140 million miles if I reduce those things there. Think of it like a fraction, 60 over 2,800, and I could keep reducing down until I got 3 over 140. If I wanted this from our school site, I would have a 3 to 140. It'd be a little bit of a funky little measurement there, but it would allow me to recreate the solar system in that space. In the textbook, I know for the teacher's side, it talked about perhaps using a space like a gym, and a gym having about 100 feet across. That gives you a little bit better number to work with when you're talking about 100. But we went ahead and just did 60 here. Up to you how you did it in class. Again, that's just more a review of what you might have done in class today. Getting on to the third section. The third section was a little interesting because it said that you have a rectangular park that is 120 feet long, we'll say 120 by 75 feet wide. Okay, so that's what a rectangular park looks like, 120 by 75. And it said that Lynn made a scale drawing of the park with a scale of 1 to 15, ended up making it in the shape of a 5 by 8 shape there. Diego made one with a scale of 1 to 180 and also ended up with a 5 by 8 shape here. It says explain or show how each scale would produce an 8-inch by 5-inch drawing. Alright, that becomes a complicated part for this one here. Let's look at Lynn first of all. So for Lynn, when we're talking about Lynn's drawing, we can see that if the scale is 1 to 15, and I'm dealing with numbers like a 75 and 120, if I take her 75, 120, that's my actual, right? This is my actual size here. She's using a 5 for one length and an 8 for the other length. And our scale factor she used was 1 to 15. If I multiply 5 by 15, I end up with 75. If I multiply the 8 by the 15, I end up with 120. Those you'd look at and say, no problem, that makes sense. She's just taking the original value, she's reducing it by 15 to make that scale factor, or dividing by 15 to make that scale factor 5 to 8. No problem there. But when you got to Diego, Diego's was a little different, wasn't it? Diego had the same numbers of 5 to 8 as well, but when you look at his numbers, they just don't seem to be quite as nice there, do they? It's just not quite the same thing. But yet, at the same time, it's not that different. Let's take a look. If we do the same pattern we did before, if we take his 5 and we take his 8 and we multiply it going the other way, because instead of going from the original to the scale factor drawing, the copy, we're going from the copy back to the original. If I multiply both those numbers by 180, here's what you end up with. You end up with 5 times 180 is 900, and 8 times 180 is 1,440. So that's my length and my width, right? Multiplied by 180. Think of it this way. If I put a fraction bar there to say, let's make this a fraction, length times width, does that equal my original? My original was 75 by 120. That was my original size, right? 75 by 120. So to decide if those are equal, I could do some cross multiplication here, multiply those two numbers, and if they are equal, then we would say, yes, it's the same scale factor, same scale drawing, and it worked just well. And when you do that, you end up finding that these two numbers multiply by each other, and those two end up both being 108,000, which means that since they both are 108,000, that their scale factor actually works, and it works out well. It's just a different approach there to making that work, but it does work for this guy. Number 2 said to make another scale drawing the same parking lot on a 1 to 20. So again, we're looking at having the original was 75 to 120. That was our original one there. And then that 75 to 120, we're going to go with a 120 scale factor there. So because we're reducing it, right, we're going smaller, we're going to end up dividing by 20 instead of multiplying, because that's our original. To go to a scale copy, we're going to drop down. So I'll take my length, 120, and divide it by 20, which gives me 6. And then I could take my height here, 75, and divide it by 20, which gives me about 3 3/4. So if I was to draw that out, it would look something like this. I'd have a 6 there and 3 3/4 here for the size of that new scale drawing in this case. That's what it looks like there. All right. So just give you an idea of what that would look like, how you would do that in class today. Just a quick recap review. So our summary for this lesson says that in some scale drawings, the scale specifies 1 unit for the distance of the drawing and a different unit for the actual distance. For example, a drawing could have a scale of 1 centimeter to 10 kilometers. Okay, so sometimes there's an actual, it's going to scale specifies a unit. Sometimes. In other times, the scale does not specify any unit at all, like we did in these samples. So 1 to 100. So you want to pay attention to that, because it's going to have an impact on what you're doing with your picture, as you may have to convert from things like inches to feet, or if it's just inches to inches. You see, these are all equivalent. 1 inch to 200 feet, that's easy to do, but if I want to make it inches, well, there's a difference between 200 feet and 2,400 inches in terms of how it's written, but in reality, it's the same thing. So if I want to have the same scale factor, the same scale units, I could do 1 to 2,400. But if I want to change it into inches to feet, then that's what you have there. So that was essentially what the lesson was about today. So let's take a look then at our lesson here for looking at the homework today and see what we have. When we look at our homework, the first one says that a scale drawing of a car is presented in the following 3 scales. Order the scale drawings from smallest to largest and explain your reasoning. It does give us some additional information here. So we're going to be going from 1 inch to a foot, 1 inch to a meter, and 1 inch to a yard. Knowing what I just know about measurements, if a foot is about this long, let's just pretend, we know that a meter is longer than a foot. But we also might remember or know that a yard is just a little bit shorter than a meter. So when I'm just looking at the actual shapes of these objects, a yardstick is basically 3 feet, right? But a meter stick is a little bit longer than a yard. So it says here there's 1.1 yards in a meter. So it's a little bit longer, okay? Now what we said before is that the larger the number, the smaller the drawing will be, okay? So the larger the number, the smaller the drawing will be. So in terms of which one's the larger, which one is the larger length? A foot, a meter, a yard? We would say a meter is the largest. So that's going to end up with the smallest drawing. The next largest would be C. And our smallest, which actually would end up being our biggest picture, A. So my order would be something like this, because the larger the number, the larger this value, the smaller the drawing is going to be. So we would say B, C, A to go from smallest to largest for the scale drawing. All right, here we go. So number 2, which scales are equivalent to 1 inch to 1 foot? Select all that apply. So these are different ways of thinking about the same thing. 1 inch to 1 foot. Well, how many inches are in a foot? We would say 12. So is 1 inch to 12 inches equivalent to 1 and 1 foot? Yes, it is, indeed, because of how that works there. For B, we would say 1/12 to 1. This is like going the other way. So 1/12 of an inch, does that get up to 1? If I multiply by 12, because there's 12 inches in a foot, I end up with 1. So we would say, yep, that one works there. No problem. For C, C is a little different. While it has that 0.2 there, 0.2 is 12 over 100. That's the idea. But this is probably going to be something more for centimeters. Plus, we're going the other way. You're not going to have more than the other. Plus, a foot is not on a 100 scale, so it's not going to work there. It's a kind of a tricky one to throw at you a little bit, but the answer is no. For this one, 5 to 60, well, 5 inches. 5 inches. Let's think about this. If I had 5 inches, all right, if I have 5 inches and then going to 60, we would say, well, is that going to get me to 60? How is that going to work there? Well, this is 1 to 12 in terms of inches. Is that equivalent to 5 inches is the same to 60? Well, look at this way. If I went from 1 to 5, how would I get there? I could use multiplying 5 as a way to get there and check the bottom out. What's 12 times 5? It is indeed 60. So because that works out with the same multiplying factor there, we would say D does actually work. Looking good, no problem. For E, what we have here is we have 36 inches to 3 feet. Could that work out all right? Well, it has the potential to work out all right, but it's actually going the wrong way just because of how it's written. You see, because there aren't units involved, we don't know what's going to what. We just know we're going from a lot of them to a little bit. And in our actual one, we're going from a little to a lot. So it's going the reverse direction. So we would say that's just not going to work out too well there. Okay? And then finally looking at F, from 9 to 108, we're going from small to big. That's looking pretty good there. We could again take a look at how am I getting from one to the other. Well, we're going to be using a factor of 9 or dividing by 9, how you want to think about that there. And so you do 9 times 12 and you end up with 108. So that 9, 1 times 9 gives you 9. That's going to work because that scale factor of 9 is working with both numbers there. Number 3, a model airplane is built on a scale of 1 to 72. If the model plane is 8 inches long, how many feet long is the actual airplane? Now notice our scale has what again? No units. No units. It's 1 to 72. So we don't know what we're going to be looking at, except we can't do inches and feet. We have to pick one. Okay. Now because we're using the model first, the model is inches, which means we're going from, if we call this all inches here, we're going to be going from 72 inches down to an 8-inch type of idea. Does that make sense a little bit? So we're going to be doing our model 8 times the 72 to get to the actual thing, which ends up being 576 inches. So I take my model length, 8 inches, times my scale factor 17, but I'm still in the world of inches. The question though asks how many feet that is. So to find out how many feet, I need to divide by 12. And I divide by 12 because there are 12 inches in 1 foot. Okay, 12 inches in 1 foot. And 56 divided by 12 equals 48 feet is what I end up with there. If you want to draw this out in a different way, think of it like this. 576 inches times, and then watch this, ready? I have, I'm doing feet here, right? So in one, I have 12 inches in 1 foot, right? That's my scale there. 1 foot to 12 inches. When I multiply this out, the inches cancel each other out, and I have 576 divided by 12, which we said is 48. And what word is left? The inches are gone. The word that's left remains is feet. So I have 48 feet. Looking at number 4. We have quadrilateral A has side lengths 3, 6, 6, and 9. Let's just draw it out real quick. 3, 6, 6, and 9. So I'm going to say 3, 6, 6, and 9. I don't know if that's the actual shape, just making one that works for me. 3, 6, 6, and 9. Great. B is a scaled copy of A with the shortest side length equal to 2. So we have another one, a scaled copy with a length of 2. Alright, so you put a 2 right there. Jada says since the side lengths go down by 1 in this scaling, well, so far, 3 to 2, the perimeter goes down by 4 in total. Do you agree with that reasoning? You have to decide, is this really going down by 1? It might be going down by 1 when we use addition or subtraction, but remember, we can't use addition and subtraction when doing scale factoring. We use multiplication or division. So to go from 3 times a number and end up with 2, we find out that our scale factor, when we divide both sides by 3, is actually 2/3. Well, if that's the case, if our scale factor that we're playing with is 2/3, and I look at a 6, to do 6 times 2/3 to get my new length here, I have 6 times 2 is 12, divided by 3 is 4. That makes that length 4 and that length 4. And looking at the 9, if I did 9 times 2/3, 9 times 2 is 18, divided by 3 is 6. My new scale drawing or scaled copy for B would have lengths of 2, 4, 4, and 6. Well, the perimeter of the original, all these add together, was going to be 24, and the new perimeter ends up being 16. So, is our perimeter going down by 4 in total? We would say, no, it is not going down 4 in total. And Jada did some poor math, so she needs to check her work one more time to figure that out. Number 5. Polygon B is a scaled copy of A using a scale factor of 5. Polygon A's area is what fraction of polygon B's area? So to find our area, what we look at is we say, well, our scale factor is going to be, in this case, is times 5. Well, area is your scale factor squared times your original area, and that becomes your new area. So in this case, if the scale factor, in this case, is 5, we would have 5 squared, which is 25, right? So that becomes 25 times the original equals the new. So what fraction of the polygons B is going to be that one? We would say it's going to be 1/25 of what we started with, okay? Because we're reducing it down, it's going to be 1/25 in size. So we take 25 and we just flip it on over, and we have the inverse there for 1/25. And finally, the last one, number 6, figures R, S, and T are all scaled copies of one another. Figure S is a scale of R. t, and so on. Figure S is a scaled copy of r using a scale factor of 3. T is a scale copy of S using a scale copy of 2. So what's happening here? Well, what we're saying is we have r goes to S, and the scale factor from r to S is times 3. But to go from S to T, we have times 2. All right, so that's where we are so far. Let's apply that over here and rewrite this out here one more time. So to go from R to S, it's times 3. To go from S to T, it's times 2. All right, so when we're going this way, we're multiplying by 3 or 2. To go this way, we're dividing by 2 and dividing by 3. So let's take a look here. To go from T to S, we would say we're going to divide by 2 or multiply by a half. Same idea. Either way, it works for me. Times a half or divide by 2. Two ways of thinking about it. For S to R, we're going to either multiply by a third or divide by 3. Same idea. R to T, we're going times 3 times 2, which becomes times 6, multiplying by 6. And from T to R, we have not just times, we're not dividing by just 2, we're dividing by 2 times a 3, so a 6. So we're going to multiply by 1/6, or we could say divide by 6 there. And those become our solutions for how this works, going from one shape to another shape and doing it a couple different times. Hope that helps you out a little bit today with today's lesson, and good luck. See ya.